All right, so now it's time to welcome our speaker, Dawen Liang, from with a senior researcher at Netflix Research. Dawen did a PhD in Colombia with David Blay, if I remember correctly. I forgot my notes, sorry. That's correct, yes. And is now an expert on recommender systems, and I let now Dawen speak on his take on recommender system and Bayesian, how you could use Bayes to make better recommender systems. Thank you, Dawen.
Okay, thank you. Let me, okay. So thanks very much for having me here. It's my pleasure to talk about Bayesian and recommender system, even though you might not actually like what I'm gonna say about Bayesian and recommender system, but I think it's good to have this conversation. By the way, I'm not sure how the Q&A is gonna work, but I heard this format is normally very interactive. So I guess if there's any question coming up, you can just feel free to interrupt me and ask questions, and then we can have a more engaging conversation if that's how it works. Since I don't have like particular slides prepared for like questions answering, so I think we can just have question answered on the way. So yeah, let me also hide this active speaker window. Okay. So yeah, as you can see, the topic for today's talk is Variational Autoencoders for Recommender Systems. The subtitle is it's very long, a critical retrospective and a hopefully optimistic perspective. So basically, this talk will be about the, well, at least the first part of the talk will be about our paper from 2 years ago about using variational autoencoder for collaborative filtering. And as you can see from the subtitle, this talk probably consists of 2 parts. The first part, as you can see, is a critical retrospective. So basically, I'm gonna kind of go over the slides I made 2 years ago for this paper, and also provide my 2020 commentary as like a critical retrospective. I think since I'm going to talk about my own work, I think I can be brutally honest without any consequence. And also, I think it's good that when you look back at your work from a couple of years ago, you can actually realize there is something, I guess you can say, you're not very satisfactory about, even though back then you are very happy about the paper, which I think is a good thing. Okay, so basically a little bit of a background. So in this paper, we mostly deal with what I think commonly called in the field as implicit feedback data. So what does that mean is basically means we observe in the form of a user item interaction matrix. So here I have an example with a couple users and a couple items. And for each user item pair, we can either observe a user interact with the item. So here I mostly will be use a word click, even though it can mean many other things. But just for the sake of concordance, I just say click. And if we observe an interaction between user U and item I, then we observe A1. And otherwise we observe, I mean, it's really a question mark because it can either, like if we don't observe interaction between certain user and item pair, it could either be because the user is not interested in the item, but it could also be the user is not aware of the item. So that's why it's a question mark, but also in reality, I guess people normally treat this as the question mark as 0. So here, basically, each row of this matrix is what I would call a XU, which basically represents the feedback from user U, and it's basically a vector of binary values. And one crucial part about implicit feedback data is that when we model this type of data, we use both the observed ones and the missing zeros, precisely for the reason we actually don't know what zero really means. And I think actually how to understand the zero means is a very, I guess, important and kind of open question for implicit feedback data. And so also, in particular, this paper will mostly be deal with top N recommender system, which basically means we hope our recommendation is good in the top N, which is like, I guess, 10, 20, or 100. Okay, so this part will mostly be a recap. I think maybe a lot of you have already quite familiar with this work, but I think for the sake of completeness, I will still go over this, and also feel free to ask me any questions. So basically, I think there are many ways to interpret a variational autoencoder. One way I find particularly useful is to view variational autoencoder really as a combination of a probabilistic model and a approximate inference. So what do I mean by that? So again, we start with the model. So here, the model is what I would call a multinomial nonlinear factor analysis. So the generative process in this case is for each user U, we first sample a latent representation ZU from, I guess, a standard normal distribution. And then we pass this ZU through a nonlinear function, i.e. a neural net. And then we basically take the exponentiate and then normalize it so that it sums to 1. So basically here pi ZU gives us a, I guess, a probability. Then later we can use to sample from a multinomial distribution. So that gives us our observation XU, which is that binary vector that I defined in the last slide. So now we have this generative model. We want to do posterior inference. So in this case, the posterior is, of course, intractable. And I guess the standard way to do approximate inference is we introduce a approximation, a variational distribution Q of Z, which will try to be as close to the true posterior P of Z given X as close as possible. So here we have chosen a particular parametric family, which here we use a normal distribution. And here the mean and the variance are both free parameters. So this is, I guess, the standard variational inference. However, you can probably see the problem in this case is that we basically need to maintain a set of free parameter for each user. And that's probably not the most ideal case because you might have many users and you want to, yes?
Sorry, we already have one question from Pierre-Henri Simon. Is ZU a potential vector of prediction?
It's
ZU.
ZU, yes.
That's what is in the question. I'm not sure what. Yes, but ZU, exactly.
Yes.
Yeah, he says, is it a potential vector of prediction? I'm not sure I understand the question, to be honest.
What do you mean by a potential vector? I guess.
I don't know. Pierre, do you want to elaborate? Yeah, I don't know what he means by that either. The person was...
I mean, I guess we can maybe keep going, and if you can type in the chat about what you mean by potential function, I mean.
Yeah, that's okay. He's answering. Okay, I'm afraid you do not hear me. No, Pierre, we told you at the beginning of the talk, you have to type the question, and everybody's on mute except the organizers and the speaker. So please proceed, Dawen, and maybe. Okay. Just give an example of value for ZU regarding XU.
So I guess you can really think of ZU as um, so I guess in a standard latent variable probabilistic model, you would have some observed value, which in this case is X. And then you would also have some um, value which is latent, but you define that it's kind of like you assume it exists, but you just did not get to observe it. So ZU in this case is a unobserved latent variable. And really the goal of the inference is trying to reason about those unobserved values through the posterior, which is P of ZU given XU. I hope that kind of gives a little bit of answer.
Yeah, I think it does. Yes, I think you can
Okay.
proceed. Yeah.
So yeah, so like I said, really the goal of the inference is trying to reason about this posterior P of ZU given XU. However, it's mostly intractable for any reasonably complex model. So I guess the standard strategy is to use a variational distribution Q of ZU to approximate this intractable distribution. So we have the choice of actually using free parameter to define this distribution. Here in this case, the free parameter would be the mean and the variance of this Q distribution. However, this means the number of parameter will actually grow with the number of users, which is not the most ideal case. So alternatively, we can also define a data-dependent inference functions rather than just define a per user set of parameters. So what do I mean by that? It's basically very similar. We have a very similar form of Q distribution, but rather than having the free parameters, we actually now have the mean and the variance both be a function of the input. So here again, both the mu function and the sigma function are nonlinear, could be nonlinear functions, i.e. they can be a neural net. And when we actually put both together in this graphical model, we can actually kind of see that we start from the input X, and then this pass through the function for mu function and sigma function, which gives us the approximating posterior Q of Z giving X. And then start from that, we can go through the generative process, start from Z to X. So basically, if you look at what's shown on the right, it kind of looks like a autoencoding structure, and hence the name variational autoencoder. So you essentially have a structure that's like a standard autoencoder, but in the meantime, you are also performing approximating posterior inference. So that's why it's called variational autoencoder. At least this is like one way to interpret variational autoencoder, which I find very helpful. Is there a question I heard? Okay.
I don't see any question at the moment.
Okay, no, I just saw you said something. Okay, so basically you might see that I used a multinomial likelihood, which I think now is probably more like the standard choice, but I think back in 2018, at least back at that time, a lot of the recommender system literature still mostly deals with like the square loss or weighted square loss, and I was kind of puzzled by that choice, but basically I want to argue why actually multinomial is a very good loss function for recommender system. So first of all, I mean, it's not that uncommon loss function. It's been used everywhere else. It's commonly used in language model, for example, latent ratio allocation. And also actually even a lot of those neural language model use cross entropy, which is also a form of multinomial likelihood. It's also used in the multinomial logit choice model, which is commonly used in economics. And furthermore, I would like to argue that multinomial is actually a very close proxy to the top n ranking loss relative to the other choice like Gaussian or logistic. So basically, the multinomial likelihood actually, because if you look at the form, it has a probability that has to sum to 1 over your entire item set. And the likelihood will get reward if the model put probability mass on non-zero entries in your click matrix. And since this pi of zu must sum to 1, you can kind of imagine there is a competing nature between different items to compute for the very limited budget. So in effect, this basically will push the non-zero entries in your observation higher in the ranking. So even though people in the recommendation literature, they like to talk about point-wise versus list-wise loss function, even though multinomial, you might consider it's more closer to point-wise loss function, just because this normalizing over your entire item set to make sure this pi sums to 1, that also kind of gives you a list-wise property.
Dawen?
Yes?
Sorry, we have 2 questions.
Okay.
The first question from Tan Dung, sorry if I don't pronounce your name correctly. In cases of limited amount of data, would you think the variational inference is still applicable to find the approximate Q phi of ZU given XU?
You said in the case of limited data?
Yes.
Well, I think that's a question that deserves another talk, but I think basically you can think in this way. You can always do variational inference no matter how much data you have. Actually, you might even argue when you have little data, you would actually even want to use variational inference over other methods, just because when you have little data, your model can easily overfit. But then when you perform variational inference, which I will show the objective later, you actually also put a pretty strong prior constraint, which means your model will likely not extrapolate too crazily with small amount of data. But I guess this is also kind of a subjective area. But I don't really think this should stop you from using variational inference if your data size is small.
Thanks a lot. And then we have a question, which is maybe a remark from Kenneth. I think there's a problem of notation in the previous slide. It should be bar X, since it is an approximation derived from the latent space.
Here?
Not sure. Where is it bar X? I'm not sure I understand this comment myself. So.
It's very possible that I might have some typos.
But why a bar? I don't know.
I hope at least I
just after that, Kenneth says. Just after that, he says. Yeah. Yeah, I don't see the typo myself, but
okay. Yeah, I mean, it's very likely I will have typos throughout the talk, but I just hope I get my message across. And if there's anything confusing, you can also let me know.
Okay, let's go on then.
Because we all make our slides in the last minute, so there has to be typo. Okay, so yes. How do you train a variational autoencoder? So this is the objective function. I will omit how you actually can derive it. It's standard derivation you can find in a lot of other papers. So you can kind of see variational autoencoder, the objective of a variational autoencoder as like those 2 components. So the first part is you can kind of view it as expected log likelihood, which you can also interpret as negative reconstruction error. And then the second part is the KL divergence between your approximating posterior Q and your prior P. So this in some form provide I guess, a regularization in a standard empirical risk minimization type of loss function. So note that in the standard version of autoencoder, we don't have this scalar beta. But since you interpret this as a regularization, it only seems natural you can also have a regularization strength, which in this case is a beta parameter. And in this particular case of VE for recommender system, we actually set this beta to smaller than 1, which means it actually gives a weaker regularization as in a standard version of autoencoder. So as you can see from this objective, when you set beta less than 1, you practically relax the prior constraint on your posterior cube. So I mean, guys, the reason I kind of argued in the paper is that we don't necessarily need all the statistical property of a generative model, at least for recommender system. We don't really need the we basically don't need the model to be able to perform ancestral sampling to generate realistic data point, whatever that means. We actually care more about fit the data better and also make better prediction. So basically, in practice, we actually observe that if you actually don't set this beta value to smaller than 1, you probably will not get a very good performance. But you might ask, like, how can you select this beta, which admittedly is not an easy task because, I mean, training one of those models is already time consuming. And if you want to do a grid search, you probably need to train a lot of variational autoencoders, which is probably not the best way to use your GPUs. So in the paper, we presented this very heuristic approach, which is based on this very commonly used technique called annealing. So what that basically means is that you start your training procedure by starting with beta equals 0. And then you gradually ramp the beta value up all the way to 1 during your training process. So, so here basically you can see that first of all, if I don't do any annealing, which means I set the beta always to 1, I got this solid blue curve, which as you can see here is the validation ranking metric. The higher, the better. And as you can see, if I don't do any annealing, it's not very good. On the other hand, if I do annealing, start from 0 all the way to 1, I got this dashed green curve. As you can see, it started up pretty good, but then gradually goes down as you increase your beta value all the way to 1. So a very simple heuristic is basically we can kind of identify where we hit the maximum value in terms of the validation ranking metric, and then we just anneal to that point and keep that as fixed. So in this case, I only anneal the beta value from 0 to 0.2, and then I keep that fixed. So basically, in some sense, I just select the beta value by just running the model once. Like I said, this is mostly a heuristic-based approach, but in practice, I find it works actually very well. Again, I actually want to go back to this objective because actually this use of beta in a VA objective turns out to actually have a lot of interesting property and its connection to a lot of other different fields. To start with, it actually has a lot of connection with those like old school of method like maximum entropy discrimination or information bottleneck principle. In the recent years, actually, there has also been a lot of work on trying to understand the trade-off in learning latent variable model with VAE by actually setting the beta value to like a different range and to achieve different goals. And a lot of those analyses are actually done through the lens of compression theory, which I find very interesting. So for example, some of those work, variational lossy autoencoders, beta VAE, and finally this rate distortion analysis, which I showed a plot here. I actually highly recommend this last one, which is I think the Alex Alemi et al. At SML 2018, fixing a broken elbow. So in this paper, they presented a rate distortion analysis point of view of how you can actually setting up this beta value in the 2D plane. And effectively, by changing your value, you are really moving in this plane, and then you can actually identify what you find the best beta value by different application scenario. Okay, so I think I saw another question. Is there?
Yes, sorry. Serdar asks, is beta bounded by 1 and why?
No. I mean, so beta here is, like I said, it's really a regularization parameter. If you set beta larger than 1, it's actually going to be what essentially, in this case, this beta VAE paper. I'm not sure if you can see my mouse. So let me see if I can turn on a pointer or something. Okay, I don't know how to turn on the pointer. Sorry, I'm not very familiar with Zoom. But basically, yes, you can set beta larger than 1. It's not really bounded by anything. In fact, in this beta VAE paper, that's precisely what they did. They set the beta value to be much larger than 1. And what that does is basically it enforces your approximating Q function to be very close to the prior as compared to the likelihood. And because your prior is really a standard normal, which means different dimensions are independent, by setting beta larger than 1, they are basically hoping to achieve the goal of disentanglement, so that the learned Q function will also have independent dimension across dimensions, so that you can hope that each individual latent dimension will capture a very unique aspect of your data. So that's how they can achieve disentanglement.
So I think Alberto was asking the same question. He asked, have you tried beta larger than 1, and is it always worse than smaller than 1?
Oh, you mean for recommender system?
I guess.
Yes,
he says yes.
Okay, I mean, it's been a while. I probably have tried, but basically, really the point here is, as you can see, you really, at least I would argue in recommender system, you would really want to maximize the first term here, and also you hope your model not to be too influenced by the second term. I cannot remember exactly if I tried beta larger than 1 or not. But I would guess it's probably not going to be as good as setting beta equals 1, in which case it's also not as good as setting beta less than 1. But again, I mean, all my code is available on GitHub. If you are curious, you can feel free to try and let me know. If actually it turns out beta larger than 1 is also good, then maybe that's another paper.
Thank you.
Okay, thanks. Any other questions before we move on?
I might throw in one. My intuition says if beta equals a half, you're actually squaring the likelihood. Do you agree with that? And you're actually double counting the data and undercounting the uncertainty.
If it's half, yeah.
So
yeah. I mean, I think if you set beta less than 1, you're in effect you are putting more emphasis on your data and
tightening the posterior more than the data would normally allow for.
Yes.
Thank you.
Okay, I realize actually, well, it's already 30 minutes, so maybe I should speed up a little bit. But so basically, here are the part that I'm going to be, I guess, slightly more critical. That's what my title suggests. So basically, in my 2018 slides, I have this particular page which I said, oh, why do you want to use VAE, or rather, why do you want to be Bayesian? Because, well, especially in a field that's largely pragmatic, why do you want to be Bayesian? And I gave those 3 reasons, but I'm going to present those 3 reasons first, but then I will maybe discuss each individual one in detail in a critical manner. So the first reason, at least I presented back then, was that this VAE actually generalized linear latent variable, latent factor models.
Dawen?
Yes?
Sorry, again, another question about beta. So can we use beta between 0 and 1 to get good model performance?
So I guess really depends on what you mean by model performance. Like, so the beta really gives you an additional degree of flexibility to actually tailor to whatever the model performance you care about. Like if you care about faithfully learning about the data, then you should maybe set beta to less than 1. But if you care about some other property of your model, then maybe you should set beta larger than 1. Again, I highly recommend checking out this Fixing a Broken Elbow paper by Lemmy et al. In 2018. They provide a very comprehensive analysis in the form of rate and distortion analysis trade-off from like a compression and information theoretic point of view, which is very good. Okay, so I guess moving on. So so basically, I hope it's reasonably clear that in VAE, again, if you remember, I have those like nonlinear functions, but if you actually replace those nonlinear functions with linear functions, you're basically going to recover the standard matrix factorization / latent differential allocation as like special case. And then the second reason why I find variational autoencoder to be very attractive, at least back in 2018, is that if you actually ever used a standard matrix factorization type of model, you would know that when you are giving, like once you train your model and now you are giving a new user, you actually need to perform a small iterative process to actually learn the user latent factor for those new user. And then you can start performing recommendation. However, with VAE, you don't really have to do that because if you remember earlier, we have those function, mu function and sigma function. Even when giving a new user, we don't actually need to perform any additional optimization. All we need to do is really just make a forward pass through the inference function and the generative function. And then we will have the score that we can use to make a recommendation. And lastly, I argued back in 2018 that I think recommender system is more of a small data problem rather than a big data problem. So what do I mean by that? If you imagine, like in a typical recommender system, people normally think of this as like a big data problem because you have a lot of users and also you have a lot of items. However, it's not necessarily the case because even though you have a lot of user and a lot of items, each user really only click on a very small amount of items. So that's why I argue it's really more of a small data problem. I will later provide my 2020 commentary to that in more details. But yeah, basically those are the 3 points that I presented back then as to argue why I like VAE or rather Bayesian. So now I'm gonna provide my 2020 commentary. Start from the second point. So the second point where I argue you don't actually need an iterative process, you just need to evaluate 2 functions to actually make a recommendation. This is essentially what I think now people call a amortization. And first of all, amortization is very important in many applications. In this particular case, amortization helps us prevent the case where you actually need to maintain a per user parameter, which means if you have a lot of users, your number of parameter will grow very fast. So, but even though amortization is very useful, it's actually not variational autoencoder specific. I mean, you can even do a linear model with amortization, which I will get to in the second part of the talk. And another thing that I did not mention is during the training, I also performed Dropout, which I will also get to, I guess, in more details in the second half of the talk, and I would argue why dropout is actually why it's particularly attractive for recommender system. And also, when we perform amortization inference, essentially you trade off a per user parameter with a function that hopefully you can generalize to all the users. But by doing that, you also introduce a additional amortization gap or amortization error, which is something we should also keep in mind of. So this is basically one point that's not really about VAE specifically. And then the first point that I presented was that this VAE actually generalized linear latent factor model, which I think it's still correct. But I also want to point out that what's really happening here is, like I mentioned in the last slides, when we perform amortization inference, we are effectively kind of sacrificing the quality of our posterior inference, since we are using a amortization function rather than having a fixed free parameter that we are free to optimize. But on the other hand, by using this, we are also able to perform posterior inference with a much more complex model, in this case, a neural net, as opposed to a linear model. So basically, on the one hand, we kind of lost some of the inference quality, but on the other hand, we gained by increasing the expressibility of our model. So it's really a trade-off. And in this case, we realize the trade-off pays off. By using a much more complex model, we actually are able to get some good results, even though the quality of the inference actually degraded. And finally, about this point about recommender system is more of a small data and big data problem. It's going to be I guess, more complicated topic, which I will get to in my 2020 commentary. So in the paper, I had this plot where I showed that I basically break down all the users by their activity, and starting from left to right, each plot has an increasing level of user activity. By activity, I basically means how many items you clicked in the data. And here I basically compared two versions of the autoencoder. So the blue one is the non-Bayesian point estimate autoencoder, and the green one is the variational autoencoder that I just presented. And my point here was basically to show that, look, when you're faced with low user activity data point, the variational autoencoder tends to outperform the point estimate version of the model. And actually, as you get higher, you may actually get a reverse result. This was what I presented in the paper, which I think is not wrong, and also not very surprising, because if you remember, in the objective function, the second term is basically a prior regularization, and it does indeed prevent the model from like extrapolate like crazy with small amount of data. But on the other hand, it also kind of hurt the performance for more active users, just because when you have a lot of active click, you actually, the likelihood term should dominate, and you should not really care too much about how the prior regularization would behave in this case. But I guess a bigger point I want to make, at least this is my hot take from 2020, is that I think recommender system is a big data or small data problem is not exactly really the right question to answer to ask. So exactly what do I mean by that? Again, I want to emphasize that if you are only thinking in terms of like small data, in the sense that you don't observe a lot of click, versus big data, which means you actually observe a lot of interaction from this user, of course, Bayesian approach is definitely among the answers, but it's not the only answer. There are many other approaches which will achieve the same result through proper regularization. But I guess my bigger comment is that this question of small data versus big data problem is actually kind of missing the picture, which is that a recommender system is basically a system of interaction. You don't have a static small data or a big data problem. Rather, you actually have a, I guess you can call it a organic interactive system. And in the system, our goal, you can argue our goal is interventional in some sense. So what do I mean by interventional? I basically mean that your ultimate goal is really to present low activity users with good recommendations so that they would like to be more active. So I guess you can kind of think of this really as an interactive process where you start with small data, and then through interaction, you hope that you would actually get more data. So it's not really a distinction between small data and big data, and then we want Bayesian to be helpful in this case. It's really just, I think the bigger picture is holistically, those are really belong to the same process. But I also, that doesn't mean like Bayesian method would not be helpful at all. On the contrary, actually, during the interaction process, as you probably know, in a lot of the recommender system, you would like to kind of trade off the exploration with exploitation. And during this exploration, actually taking uncertainty into account is the crucial part of the entire system. So this starts to actually get to the territory of bandit and reinforcement learning, which is not really the scope of this talk, but in all of those areas, taking uncertainty into account is very important. But again, taking uncertainty into account does not mean you can only do Bayesian. There are also other type of approaches, but I just want to point out that still the Bayesian uncertainty can be used in a very different way. Okay, so that's my, I guess, 2020 hot take. Any questions?
I don't see any question at the moment.
Okay, so let's move on. So how well does it work? Normally I would present like a couple of tables with numbers showing that my method beats all your methods, but it's actually not as relevant now because this paper is from like 2 years ago and a lot has happened. So I don't think that's actually as relevant. Instead, I'm also going to take, I guess, a more critical retrospective about this analysis that happened last year, which also drew a lot of attention. In case of you haven't heard of this, is basically, I guess, a Rex's paper from last year where a bunch of researchers did some meta-analysis. So let me just quote from the abstract. So they basically kind of examined a lot of the deep learning neural network-based recommender systems. And specifically, they considered 18 algorithms. However, only 7 of them can be reproduced with reasonable effort. And then 6 of them can often be outperformed with comparably simple heuristic method. And then the last one, yes? Hello?
Dawen, sorry, there was a few questions. When you talk about interventional, are you pointing toward causal mode LS?
Yes, I think when I talk about interventional, yes, I'm mostly talking about from a causal perspective. Even though that's a much deeper topic, which yeah.
And then that the same person are just A/B testing.
I would argue it's really both. So first of all, A/B testing is definitely, I guess you can consider as like the ultimate test bed. But even before you perform an A/B test, you would actually want to know what would have happened had you put this online, which basically got to the territory of counterfactual evaluation or of policy evaluation. And you actually want your learning objective offline to match whatever the objective you are pursuing online. And if you can actually do that effectively, you don't have to, well, basically, first of all, that can save you a lot of effort because A/B test is expensive. If you can actually make a lot of choice before you even start your A/B test, that will save you energy, resources, and et cetera, et cetera. So yeah, I think it's not really like one thing or the other, but I think it's good to really consider both, like consider from a causal perspective, but also eventually you want to have a good A/B test performance.
And one last question for now. Justine says, when you say your system is interventional, are you investigating causality in recommendation systems? It's a bit the same question. But,
yeah, I think it's kind of the same question. I mean, I would argue by interventional, I really mean it. I basically meant that you should really think about recommendation from this counterfactual perspective. And really, I guess one more thing is that it's also interventional in the sense that you hope, your goal is to hope actually you can convince the low active user to be more active so that you would able to actually observe more interaction, and then you are able to have this very healthy organic interactive process. So that's another level of meaning when I say intervention. Okay,
I
so
guess we can move on.
Yes, let's get back to this. But basically, well, there's this analysis, and most of the baselines, well, most of the algorithms can be outperformed with comparably simple heuristic method. And then the remaining one, even though it clearly outperformed the baselines, it did not consistently outperform a well-tuned non-neural network ranking method. So in this case, you probably heard that the variational autoencoder is that remaining one, which luckily outperformed the baseline, but did not consistently outperform a well-tuned non-neural linear ranking method. So I will actually get to why I think it's not too surprising that a non-neural network linear model can actually perform so well, I guess, later. But I would actually provide my my thoughts on this. Are we really making much progress? Which I like to think in a more positive angle, which I think we are. Because I like to make this analogy that people always say that, oh, music in the 60s, 70s, or 80s, et cetera, insert your favorite period, is so much better. But it's actually not because the music in that period is all good. It's really just because whatever stood the test of times are good music. So that's how I see research as well. Like, I think research is really, I guess you can think of like research is also basically taking stochastic gradient descent, and we all gradually make a little bit of effort trying to push the research into the right direction by taking small gradient steps. I would also like to, I guess, argue that recommended system is actually a very unique field. So in the sense that, like I said earlier, it's really an interactive system, but often it's actually treated as a static system in the literature, probably because the lack of access to data, at least in academia, which is not ideal. But I think the good thing is that the good performance, even in those static settings, sometimes can still translate to good performance in the real world setting. So I think that's probably not all bad news. And which also means actually even we are just doing research in this more like in the vacuum setting, working with the static data set, it's not always bad thing. But again, you would really want to align your objective from offline training to online performance, which is why earlier I alluded to that I think counterfactual evaluation or policy evaluation is something that is very important and kind of get overlooked a little bit, at least in recommender system research. Okay. So I want to actually end this first part of the critical retrospective with a little bit of, I guess, positive ending, which is that I'm gonna quote someone I randomly met in a conference about my paper, and I think this is, I guess I would consider this is the highest compliment you can actually get as a researcher. And one positive thing I also find about this entire analysis and also the unwarranted attention that VA paper gets is that now actually a lot of paper actually start to follow the experimentation protocol that I presented in the paper, which come with the open source code on GitHub. And so at least now making comparisons across different baselines is getting slightly easier. So that's my, I guess, positive end to the critical retrospective. And if there's any questions, or I will move on to the second half.
There's someone asking in the chat, is there any interpretative meaning that can be assigned to latent variable space learned from the regsys task?
Sorry, I missed the first part of the question.
Is there any, I'm not sure when this question was asked actually, because it was not typed in the Q&A box, but is there any interpretative, I guess, meaning that can be assigned to latent variable space?
I mean, if you don't do anything special, there will be no. The answer is no, but I guess interpretability, you can kind of consider that as a orthogonal direction to what I presented here. You can certainly make your latent variable interpretable by enforcing certain structure in your latent space. For example, you can actually adapt some methodology using disentanglement to actually make your latent dimension more interpretable. But you should also keep in mind that a lot of the time when you are aiming for interpretability, you would inevitably lose, I guess, predictive power. So that's something you should keep in mind.
Okay, I don't see any other question.
Okay, so now that the first part is over, I'm gonna talk about the second part, which is what I call a hopefully optimistic perspective. So let me actually start by talk about this a friend's blog, which I highly recommend, inference.vc. So in this particular post, he talked about what he described as the secular Bayesian, which I will quote here. What he mean by secular Bayesian. So certain elements of Bayesian ways are no doubt useful. For example, engineering inductive biases explicit into a prior distribution using probabilities, divergence, information, variational bonds as tools for developing new algorithms. Posterior distributions can capture model uncertainty, which can be explored for active learning or exploration in interactive learning. So to me, my interpretation of a secular Bayesian is basically we will try to look through the lens of Bayesian thinking, but also realize Bayesian is not the only way. So basically, inspired by this secular Bayesian perspective, you can also kind of think of my second half of the talk is a secular Bayesian's view on various recommender system models, and basically through the lens of probabilistic inference, probabilistic models, you can really start to realize all those different models are just different incarnations of each other. And the variational autoencoder is one of them. It's not the only one. and it's not that different from all the other methods. So let's actually start with the most simple, basic, but also the very strong baseline matrix factorization. So recall that I have this user item interaction matrix. And the goal of matrix factorization, I mean, a lot of you are probably very familiar, but I just want to give a self-contained example throughout the talk. So basically, you are given this user item interaction matrix, and the goal is to factorize this matrix into the product of two matrices. The first one is what people normally call the user latent factor or user embedding. And then the second matrix is what people normally call the item embedding. And both matrices are of rank k. So in this case, k is normally much smaller than both the number of users and number of items in the data set. So if you look in this form, so really you are trying to approximate your data X with the matrix product of P and Q. So you can have different loss functions, and different loss function will determine how to measure the closeness of between your reconstruction to the original data. And each loss function will also come with a probabilistic interpretation. So for example, when you are using square loss, you are basically implicitly assume a Gaussian likelihood. If you are using a binary cross entropy loss, you are implicitly defining a Bernoulli likelihood, normally probably also with logistic transformation. And then finally, if you are using a multi-class cross entropy loss function, then you are implicitly defining a multinomial likelihood, or if you are actually using a unnormalized count, then you are implicitly defining a Poisson likelihood. But basically, that's what I meant earlier. From the secular Bayesian's view, you can really view everything through the lens of probabilistic models. So now let's actually go back to matrix factorization. So now let's turn our focus on the user latent factors. So as you can see, this matrix will actually grow with the number of users, which is not, I guess, the most ideal case, because you would imagine you will have an increasing amount of users, and that means this matrix will keep growing, and that's probably not the best way you can deal with this. So I'm going to introduce this kind of old method, I would argue slightly overlooked, but actually very interesting and useful idea from 2007, which is called asymmetric matrix factorization. So the way they handle this growing user latent factor matrix is actually by introducing another set of item latent factor V. So remember, we already have this Q matrix, which is a set of item latent factor. But then they also introduced another set of latent vector V. And then rather than for each user learn a user factor as free parameter, we actually construct the user factor as a average embedding of the clicked item. So what does that mean? It basically means rather than having this P of U, which means the user factor for user U, rather than setting this PU as free parameter, you actually set it as a average embedding from the clicked item. So here the sum is over all the items this user U has clicked on. So we can also write this in, I guess, in a more compact matrix form. It really just becomes the matrix product between this vector XU tilde, which is basically just the normalized, like L2 normalized input vector X. And you multiply this X tilde U with this big matrix V. So why is this interesting? So now let's actually go back to the asymmetric matrix factorization formulation. And so recall that for each user, XU, we try to approximate XU with the dot product between the user latent factor PU and the item latent factor matrix Q transpose. So we actually just plug in what we defined in the last slides of PU. And then that will actually give us execute the VQ transpose. And here you can actually just stick this into the first part of the model. And then that will actually kind of give you something similar to a autoencoder structure. And this is actually how you can actually kind of view asymmetric matrix factorization as a linear autoencoder. So you can actually even make it more general, make the notation more general. So you can actually define the function G and F. So you basically say my user latent factor P of U is the output of the function G, with the input being the input data xu. And then finally, my output xu is also through this function f. And the dimension of this middle layer, which I guess you can, in autoencoder language, we call this the bottleneck layer. The dimension of PU is normally much, much smaller than the dimension of your input data xu. So note that this is also actually a form of amortization. It's just, in this case, everything is linear. So that's also why earlier when I said amortization is actually very important, but it's not very specific to VAE, because it's actually, you can really use a similar idea to all kinds of models and formulation. So now that we have already formulated asymmetric matrix factorization as a linear autoencoder, it's actually very straightforward to turn it into a nonlinear autoencoder. So all we need to do is to change the function f and g in this case to be a nonlinear function, i.e. a neural net. And note that I also changed the input from x tilde to x, since x tilde is really a L2 normalized version of x. So you can kind of imagine that that can get taken care of in the neural net. So now that we have already defined a autoencoder, we can push one step further to get to denoising autoencoder. So why do we want to do that? So the reason is that when we replace the function f and g in this case with nonlinear functions, a lot of the loss functions that we introduced earlier can actually very easily overfit. And to prevent that, before fitting the input into the model, we can actually correct by adding some noise. For example, just using dropout. By randomly setting some of the ones in your x to 0. And so earlier I said that I think dropout is also a very important actually factor to the success of variational autoencoder. So I'm going to talk about why. So I think actually dropout is a particularly well-suited method for recommender system, because it actually kind of simulates actual testing scenario very well, because you are basically giving an input and that you randomly remove part of it. And then you want to predict the part that you got dropped out from the rest of the click history. So this is actually fits the setting for a standard recommendation system very well. And also, with that in mind, you can actually be even more creative about designing specific dropout probability to achieve certain goals. For example, you can also design very specific dropout probability to achieve inverse propensity weighting. And also, like I said earlier, the standard dropout kind of simulate the standard random held out train test scenario, but you can also simulate other potential test scenarios if you have those additional information available. I also recommend checking out this paper from my colleague Harostek, which will come out in Europe this year for an even deeper theoretical discussion around denoising autoencoder and dropout. Okay, so now we talk about the standard denoising autoencoder. We can even move one step further. So remember, in the standard denoising autoencoder, we are only going to get a point estimate for the latent user latent variable PU. But what if we want to have a distribution P of PU given XU? And that's basically where the variational autoencoder comes in. We can basically put a probability distribution on P and then perform posterior inference. And that will actually get us to the variational autoencoder, which we'll talk about in the first half of the talk. And this is also an alternative view to the model and the inference perspective that I presented in the first half of the talk. Okay, and then we can even go one step further. So actually, a lot of the work we did in the recommender system research is actually trying to reconstruct the input, which is fine, but in reality, what you really care about is really, you care about after you deploy your system, you actually want to predict what's going to happen next. So rather than trying to reconstruct the input, we can also just ask the model to predict the next one. So, and the way to achieve that is actually very straightforward. You really just change your output from just reconstructing input X to some other future next label Y. And this is also going to be more similar to, I guess, supervised learning. And also this is very similar to the neural language model, which I think started with this Yoshua Benjo 2003 paper. Later also becomes the foundational work for Word2Vec and all the other neural language model. And once you start to do that, you can also use more sophisticated architectures. For example, you can use RNN, which is, I think, commonly used in a session-based recommender system. And finally, even with this setup, you can still perform posterior inference by asking not only a point estimate for P, but also a distribution over P. And that will actually get you something of what they call the deep variational information bottleneck. This is another paper from 2017. So like I said, really, everything is connected. So the last part I'm going to talk about, let's actually go back to the linear autoencoder, because I think this part is can also be connected to another big family of recommender system models. So basically, let's just look at this. We have the output as, or basically approximate output as this input multiplied by two matrices, V and Q. So if you actually put those two together, you really just get a low rank item to item similarity matrix. So now you might ask, well, instead of a low rank matrix, can I just have a full rank matrix? And of course, you want to avoid the trivial solution, so you force your full rank matrix to have a zero diagonal. But this really actually is what the very famous SLAM model is doing. You can also think from a probabilistic model point of view, what you're doing here is really you're marginalizing over your latent bottleneck in a standard autoencoder. And furthermore, you can even just derive to show that this is really a Gaussian Markov random field, which is basically presented by my colleague Harostek last year at NeurIPS. So if you remember earlier, I talked about in that meta-analysis paper, they showed that even VAE can sometimes get outperformed by a well-tuned linear model. So now I would actually like to present why I think that's not very surprising. So why do I think a full rank linear models are a good option? So first of all, I would like to argue that linear models are probably more parameters efficient. So what do I mean by that? I guess my point is basically giving the same number of parameter, linear models are probably gonna make use of those parameters the best as compared to a nonlinear neural net. And then you also consider this full rank linear model, which is basically a model of item-item interaction. It will actually tend to have much more parameters than any typical neural net that you are going to use in a recommender system. So you combine those 2 points together, it's not really surprising that this full rank model can outperform many deep learning approaches. And there actually has been some work showing that this type of approach works especially well for more personalized domain, for example, music, as opposed to like a movie. So what can we actually go from there? This is just like an illustration. It doesn't mean you actually need to learn a neural net with like an even fatter bottleneck layer. But one thing that I find particularly interesting is, again, recall this full rank linear model. Even though it's very attractive, it has a problem that the number of parameter can easily explode if you have a lot of items. One way you can deal with that is you can actually make this model sparse. Similarly, you can also define what I like to call a full rank autoencoder. So this is actually basically inspired by this work that presented at WWW this year, learning structure of autoencoding recommenders. So what they did is, it's not exactly like this, but in effect, it's really defining an autoencoder that the bottleneck layer is really on the same magnitude as the dimension of your input. But then you also make it sparse, because otherwise your model will just learn very trivial solutions. And finally, you can even make your Markov random field to capture even higher order interaction. But I think the similarity between all those three directions are that you are really thinking in terms of imposing more structures in your high dimensional space model. And I think that's also where being a Bayesian or secular Bayesian can actually give you a lot of insight. So basically, the takeaway for this section as a secular Bayesian is that I don't think there's one superior model that kind of rules them all. The variational autoencoder is merely just one of them, and there can be many others. And hopefully I have convinced you through this section that every model can be viewed through the lens of the others. And what's good about that is, in practice, we can really just plug and play different pieces together to basically deal with whatever problem we're facing, just like Lego pieces. Okay, so I think that's all I have. Before I conclude, if there's any other questions.
No question from me, and at the moment I don't see any question from the box. So maybe you could conclude, and then you could take questions.
Okay, sounds good. So yeah, I mean, in conclusion, I think I think there might still be a place to be Bayesian even in a largely pragmatic field like recommender systems, even though the way it works is probably not how you would imagine coming in. But I still think thinking through a lot of things through the Bayesian point of view is very helpful. And also, in the second half of the talk, I hope I have convinced you that through the lens of probabilistic models, we can actually have a holistic picture about various models, and this can actually opens up possibilities for a lot of future development. So that's it. Thank you very much. Let me know if you have any questions.
Thanks a lot. If you have any question, it's the right time to ask it.
That was really awesome. Thank you. It's not often people take apart their own work.
Okay.
And I actually can't say, like, from a big company that runs a recommender system, a lot of stuff you're talking about touches on, like, there's often a tension between item and user item stuff. And I think some of the perspectives you brought at the end can I think connect between these item methods and these user item methods in a nice way.
Yeah, I find item models to be actually very, well, it's not really overlooked, but at least overlooked in those neural network style model. But it's actually very powerful. And if you actually design it right, it turns out it's also very, well, so first of all, linear model is parameter efficient, but then if you can actually blow up your parameter space by carefully designing how your model parameterize, then you actually will have a very powerful, potentially very powerful model if you can train it properly.
There's a question from Silei. Are these models running on Netflix or are they still experimental? I'm not sure you want to answer that one.
I heard something about Netflix, which means I probably will not be able to answer. What's the first part of the question?
Are these models running already in Netflix? Are they being put on production or are they still experimental?
Well, I cannot answer you that. But one thing I can say is that a lot of what I have talked about is very closely related to some of the model we're using at Netflix. That's as far as I can say.
David says, you mentioned going counterfactual as an important direction. Is there any work you think is most promising in this direction?
Well, I think there are many work that I think is promising. Well, I mean, like, so I think for counterfactual evaluation, there has been a lot of open questions because most of the time when people talk about counterfactual evaluation, they talk about, in some sense, inverse propensity weighting, which has its own problems. And it's not really clear to me for a lot of those problems how you can actually overcome the barrier, especially if you have a complex action space, which is mostly the case for any of the practical recommender systems. Well, I don't think I have a very good answer to what's promising. I mean, I think most of the methodology has been, at least in theory, has been developed. It's very difficult to actually apply those methods in practice with the setting that we are always facing in recommender systems. And there has also been a lot of work around kind of counterfactual prediction using those, like basically combining neural nets with causal inference. That's also a direction that I find very promising. But again, I think a lot of open questions still remain the same. It's not really clear to me how you can actually effectively apply some of those methods actually in practice. I think that's going to be what I will keep my eyes on, see if some of those like new methods can actually prove useful in practice.
All right, one last question, but I'm not sure I understand it entirely because the person used there are some problem in the sentence. Can you please explain in a few words the difference or similarity between Autoencoder and RBM, restrictive Boltzmann machine?
Sorry, what's the difference between?
I'm not sure because it's written between AU to encoder, between autoencoder and RBM. Okay.
Oh, okay. Well, autoencoder and RBM. Actually, it's been a while since I actually last time looked about RBM, but if I remember correctly, RBM is mostly defined as a energy-based models, if I remember correctly. Correct me if I'm wrong. I think they are definitely there is close connection, but I really see energy-based model and the latent variable model like variational autoencoders are two different classes of model that try to explain data in slightly different ways. And for RBM, I guess the problem is inference has always been hard. And also, I think nowadays when people talk about energy models, they actually talk about actually not RBM. But basically, I think to perform posterior inference in a RBM has always been very challenging.
Okay, thanks a lot. I think we have done with questions. So let me thank you again for a very interesting talk. Thank you. I'm clapping on behalf of everyone. Okay, thank you everyone for attending.